the protective envelope of the Earth's magnetosphere. And so we're very fortunate this morning in the first panel to have an outstanding group of international experts. The panel will be moderated by Jeff Chancellor. Jeff is a radiation physicist by training who works at NSBRI headquarters. So Jeff, I turn it over to you.
Thank you, Dr. Sutton. Good morning. Thank you, Dr. Alford and Mr. Abbey, for inviting me to participate here and to hosting this event. So the radiation panel is charged with discussing specific topics, the permissible exposure limits, of course, looking at new approaches to mitigating the effects of radiation on humans and Earth, the adjustment of standards on radiation levels, how can we look at the permissible exposure limits, or the PELs, and mechanisms for developing and implementing exposure limits that will enable the spaceflight program to move beyond low Earth orbit. So what I'd like to do first, and we're going to jump around these topics, and because radiation is a multidiscipline area, all of our panelists have expertise in specific areas, but because of the integrative aspect of it, they also have some expertise in other areas. And we're going to jump around and have each of them provide context on a lot of these topics. But before I get started, I'd like to take a moment and introduce them real briefly so you're familiar with them, and then we'll get started. So to my right is Dr. Valery Bogomolov. He is a physician scientist and the associate director of IBMP, and he is also the ops lead for the space medicine community at the Russian Space Agency. To his right is not Keith Single. Keith could not make it today because of a conflict with surgery. So stepping in is Dr. Jeffrey Jones, who is a professor of urology at the Baylor College of Medicine and has appointment at the Center for Space Medicine. He is board certified in urology and aerospace medicine. A former NASA flight surgeon, he was also a lead physician for the Constellation program. To Jeff's right is Dr. Robert Hines, who is an associate professor of behavioral biology at the Johns Hopkins University School of Medicine, and he specializes in studying cognitive neurobehavioral function and the effects of space radiation on neurobehavioral function and the central nervous system. To Dr. Hines' right is Dr. Anatoly Rosenfeld, who is a professor of physics and the director of the Center for Microdosimetry Physics at the University of Wollongong. He has published more than 180 papers in the field of radiation detection and dosimetry and holds 15 patents in that area also. To Dr. Rosenfeld's right is Dr. Nathan Schwadron, who is a professor of physics at the University of New Hampshire. His expertise includes the effects of radiation, the acceleration of energetic particles, and cosmic rays, and he has been extensively involved with several missions for NASA, most notable the Lunar Reconnaissance Orbiter, where he was the principal investigator of the Cosmic Ray Telescope for the effects of radiation. To Nathan's right is not Edward Simonis, but it'll be Dr. Mark Shavers. Eddie had a conflict and had to apologize. He could not be here today. But Dr. Shavers supports the NASA Radiation Health Office and the Space Radiation Analysis Group at Johnson Space Center. He's a subject matter expert and performs cancer risk assessment and risk projection for NASA astronaut crews. To Mark's right is Nicole Stott. She is a veteran astronaut and has flown on both long and short duration missions. She flew on STS-128 up to the space station, where she was a flight engineer on Expedition 20 and 21, and returned down to Earth on STS-129. Subsequently, she was a mission specialist on STS-133, which was the final flight of Shuttle Discovery, and is also a veteran spacewalker. And to Nicole's right is Dr. Igor Ushakov, who is also a physician scientist and the director of IBMP. Dr. Ushakov is a member of the Russian Academy of Sciences and was a member of the mitigation team following the Chernobyl accident. So it's a very esteemed panel. I hope we are able to communicate very well what exciting advances are happening in the radiation world and what we see are the important topics. So what I'd like to do is go ahead and turn it over to Dr. Ushakov and perhaps ask him to talk about how the Russian Space Agency manages and assesses the radiation risk for the cosmonauts. Dr. Yusupov.
Good day, dear friends. Thank you very much, Jeff, for this opportunity to be the first speaker at the panel. It is an honor for me, and I'm also surprised. When I was just a school kid, I was able to be always last because my last name starts with letter U, which is quite in the very end of the alphabet. But I'm very happy to speak first, no matter, because this is a great company, science community, and the fact is that the first panel is devoted to radiation is probably symbolic, because radiation has been and probably will remain one of the major barriers in exploring space. Last century, nuclear projects seem to be most capable. Brightest scientists were attracted to nuclear science. That is doubtless. And I think this is how it is going to be in the future. Right now, we are about to explore other planets, and the radiation factor will probably become a magnet again for bright scientists. I have to say that speaking of radiation without numbers is probably not possible. And I was trying to minimize the number of numbers that I'm going to offer here. But still, probably some of them will be a matter of concern for you. And I have to bring them up, otherwise we will be not substantiated in our discussion. I want to talk about four main questions. It is the sources, also biological effects and effects for male and females. Also the types of radiation that a human is experiencing in space is also affected by a number of factors, and probably it's not always possible to account for all of them. That is the parameters of the orbits, the phases of activity, geomagnetic situation, and heavy particles. Also the protective factor of the areas where the humans are, such as ISS. In one day, a cosmonaut usually gets about 0.5 milli-CVs. That is radiational level above the sea level. Usually, in 1 year, a cosmonaut gets about 100 CVs and sometimes 200 CVs if it is more than a year for a standard gamma and X-ray radiation, say for half a year, up to 10 rems for half a year. And this will probably be maximum. In reality, it's a little bit less for radiation levels that cosmonauts receive. In 2004, in Russia, there were some norms developed for orbital flights. And these are quite complex. I will just give you the main numbers. During the lifespan of a cosmonaut, about a little more than 1,000 milli-CVs, and for 1 year, about 500 CVs. This dosage has not been broken by any of the cosmonauts so far. However, some cosmonauts, they have had more years in flights, like 2 years and more. They are kind of getting to this limit. And even if they are going to be in space for more than 2 years, this limit is not going to be broken. So from Russian limits point of view, those are in harmony with the international radiation safety standards. What is happening here? When a carrier dosage is achieved, the additional radiation risk at one time, not protracted exposure, of course, these effects are lessened, and most hazardous when it is just one dosage at one time. Such dosage can be received, which is not a probable situation in life. Some additional risk may be about 10%. We are pleased with the Japanese and American radiational biologists' ideas on the radiational strategy, that the critical parameter of the additional risk can be 3%. And this is a good substantiated value. We agree with this approach, and we are using this in our future research. I am also grateful to Jeff. He remembered my Chernobyl past. In the end of the 80s, when Chernobyl explosion took place, and pilots participated actively in that. We had a lot of exposure cases. More than 1,000 people were irradiated, and the dosages that they have received were close to what a cosmonaut would receive during several half-year missions. So that was an emergency kind of irradiation, but it was not greater than 500 milli-CVs. And the research shows that those dosages did not cause additional oncological risks, although some other diseases came along, probably in a greater percentage than if you compare with other people who have not been irradiated. So we are trying to balance what we have received with the level of the standard and acceptable radiation level, and trying to compare the results that we received on the ground and that we're receiving in space. And this material helps us to reassure that we're actually moving in the right direction. Starting with 2004, on ISS, we are having a great experiment that is called Matryoshka. We are having a bunch of modifications of this payload. This is when we are measuring dosage of irradiation in the body of an astronaut using a phantom fake body. So we are trying to trace the distribution of irradiation along the space station and along a human body. So going above the low Earth orbit, the situation with research is going to be more complex. We will have to deal with GCRs and heavy charged particles, This is when even small dosages may be biologically much of a greater capacity and affect a human body in a worst possible way. If some physiological functions are affected here. I want to say that the career dosage that is accepted in Russia is a limit dose, which is 1,000 millisieverts or 1 CV. For a cosmonaut, this is substantial. Although it is not going above the limit, this is still the same dosage as for the nuclear plant workers, and we would like cosmonaut dosage to help them somehow, because they have also other factors that affect their well-being. Here we are using the international principle of radiational safety that is accepted by all international radiation organization. This is ALAR, principle AL. Our principle, so that we are lowering the dosage as much as possible in every particular situation. The lower the dosage, the better it is for a human being.
We can say that on Earth, this career limit or career dose can be reached in 50 years, but in space it can be reached during one mission to Mars. What is the danger associated with the heavy charged particles? I know that the specialists will expand on that. I don't want to steal their thunder, but I know that it's a newly discovered hazard that we know very little about. In Russia, we are familiar with studies that are done in the US, including the work of scientists from Baltimore University, dealing with problems in behavior and mental acuity in animals that are impacted by radiation. These studies mark the beginning of the studies that are still to come. They're very good studies. However, we also very actively pursuing this area. We have a lab that studies various biological impacts of heavy charged particles. Last year, in May of 2013, there was BION 114 mission. It's a biosatellite, and its mission plan was created by our institute with the help of our US, German, and French colleagues and Russian scientists. All in all, there were more than 40 entities that helped us to organize this project. The orbit altitude was higher than 600 kilometers, which is much higher than the ISS. Therefore, the radiation dose was 6 times larger than the levels that are impacting those who work on the ISS. So during this month-long mission, the participants of this mission received the radiation 6 times higher than the dose that affects a human on the ISS. We're going to study the results and discuss them at the conference, the Russian Academy of Sciences, at the end of this year. We invite all those interested in this subject to attend this conference. And, of course, there we will discuss impact of the radiation, its effects. And I know that we're going to be using molecular and genetic methodologies to evaluate the impact.
And in summation, I would like to say the following. I wanted to point out how important it is to coordinate and standardize our international efforts. It's very special to me that this subject is first on our agenda today, because exposure rates and the standards are good subjects to dovetail all kinds of disciplines, and we have very clear, good understanding when it comes to radiation, maybe better than in other disciplines, and nevertheless, this standardization is still to come. A good example would be the study of female exposure rates, and it's hats off to the specialists, our U.S. colleagues, our Canadian colleagues who have been studying this, and the permissible limits for both of those are 1.3 to 1.5 times lower than they are for males. In Russia, we do have similar limits as well for females up to 45 years of age. During their reproductive age, the additional exposure to the lower body should not exceed 1 SV per month. However, it's still 15 months than the exposure rates that we expose our cosmonauts and astronauts to on the International Space Station. Even this kind of example indicates that we really need to work towards standardizing our efforts in bringing them under the same umbrella. But to give another example of how well we work together, the 1 SV example that's shown by the health physics specialists in the US and in Russia and in Japan, it's 13 to 12.5 to 11% accordingly for the three aforementioned countries. That means that we're in the same ballpark, which means that there had been some good cooperation put in place. For heavy charged particles, we need a new incentive to enforce similarly strong coordination, that is towards the heavy charged particles, that we need to examine as pertains the interplanetary missions of the future. And it was very good that we heard in the introduction that we really need to strengthen the international cooperation, and radiation is right up top of the subject areas on that list. I wanted to mention that 2 books were published in Russia last year, both having to do with radiation and exposure. One speaking about planned Mars mission, another dedicated to the 55th anniversary of the space radiology area at the IBMP, the Institute. Both books exist as abstracts in English. If you're interested, I can send you those. I can even send you PDF files of certain chapters that have been translated. I would share them with anyone who's taken. Just let me know, because I'm really into getting this coordination effort off the ground, because it's very difficult, but as it is difficult, it's very fascinating to all of us. And thank you so much for your time.
Thank you, Dr. Yushkov. I appreciate you sharing the information, and I would like to focus in on, you mentioned that there was a 3% increased risk of cancer that limited the cosmonauts. That's similar to the astronauts here at NASA, and we also follow the principle of ALAR in the flight rules, where we look for a reasonable amount of exposure as possible to limit the mission. So these could be problematic as we venture out, just like Dr. Ushakov said, for a long duration mission, because the astronauts could reach those levels very quickly. So we are going to talk about how we could possibly adjust these and looking for mechanisms. But I think before we look at where we are going, we need to understand how we got to these levels also. So I'd like to ask Dr. Shavers to very briefly talk about how these standards evolved to where they are, and maybe discuss how the radiation risk is managed at NASA. Dr. Shavers?
Thank you, and I'm grateful to be here and discuss this topic. And Edward Simona sends his apologies for not being able to attend. To talk about NASA policy, NASA follows the radiation protection paradigms that were developed for terrestrial radiation workers. It's a system of more than just limitation, but also justification of every exposure. Is every exposure justified and by benefits to the individual as well as society? Also, are each individual exposures optimized? And you just heard about ALARA, as low as reasonably achievable, and ALARA is a paradigm used for keeping exposures low. However, you can see that that's fraught with an ethics question. There's been a recent IOM report on ethics for exploration, space exploration, and I think that's going to help guide us with regard to what is reasonably achievable and, in fact, what is low. The limitation part is what we usually talk about, and limitation is really, limitation of exposure is a tenet of human spaceflight. If you have a pool of astronauts who can meet a career exposure limit by being selected for a mission, then they are selected for a mission. This is only a recent issue now that astronauts who have done multiple missions on ISS are bumping up on their career limits. And this is something that we're evaluating more closely, and then research can help us with informing and addressing the policy issues of disqualifying crew. I suspect we might hear something about that. The IOM, again, has provided this ethics report, which will provide guidance on these kinds of topics. So when should we disqualify or allow more than the book limit for a specific mission? So there are many limits, and the ISS international partners have agreed to radiation exposure limits for the acute effects or tissue effects. And we have flight rules to mitigate potential impacts. The idea is to prevent clinical manifestations in a crew member that might impact them or the success of a mission. Usually we think of acute radiation syndrome associated with solar particle events, but there are also other potential situations. Depending on the mission architecture, you're going through trapped radiation belts. There are also the hopefully very small possibility of an atmospheric detonation that would impact low Earth orbit missions. So now there are questions on human behavior and performance that are synergistic with microgravity, and nutrition is one topic as well that's beginning to come up. In low Earth orbit, these are not the first concern, but in exploration, it may present new challenges for monitoring and protection from solar particle events. And as long duration alone bumps us up against exposure levels, these issues might become relevant. And then there are the late effects, including to the central nervous system and the eyes, cataracts. But mostly we're concerned about cancer, and we discuss that most frequently. For the International Space Station, there are no consensus career limits, exposure career limits for human spaceflight. The international partners, each agency maintains their own career limits. NASA is rather unique by adopting career limits for cancer risk limits based on the risk of exposure-induced death. These exposure limits are not dose-based, but risk-based. It's a 3% limit, as just mentioned, but it's also enforced at the upper limit of the 95% confidence interval. Due to the lack of much needed information, the sources of uncertainties, the individual sources of uncertainties are subjectively evaluated based on research and our experience. So NASA seeks to eliminate undue conservatism by modeling cancer risk based on the sex, age, and the individual organs which are exposed, organs and tissue. Research is targeted at reducing the various contributing sources of uncertainty from a single exposure. And then how do these combined uncertainties impact risk from multiple acute or protracted exposures? Important factors include the characterization of the expected or estimated radiation environment, the total radiation exposure, and the time rate of the exposure. Most of all, though, is the rate-limiting factors, pathways of biological responses that lead to cancer mortality. NASA maintains a human research roadmap to prioritize and create fund research opportunities to address many of these concerns. There are additional concerns which have been placed into the roadmap and put back to later time periods for evaluation, and some of those may need to be readdressed given the nature of the mission architecture. If we're going to the moon, near the moon, if we're going to an asteroid or to Mars, then we need to reconsider some of the priorities.
Great, thank you, Mark. We appreciate that. So interesting information passed on, and I think before we dive into and start discussing some of the physics of biology and how we are tackling the problem and approaching new ways to mitigate the problem, I'd like to take the opportunity to ask Nicole to provide a perspective from the astronaut office so we can hear what their opinion is, please. Nicole,
Okay,
thank you.
well, first of all, I'd like to say thanks for including me today. Thanks for including the office as a panel member. And I actually was kind of surprised to have this invitation, because anybody who knows me knows I have no expertise in the area of radiation science. And having thought about it, though, aside from being humbled to participate with the panel, I think maybe that naive perspective is okay. And I think that as I thought more about the participation here today, I turned it more into, well, the whole reason we're all here is because of me. And not me as me necessarily, but me as this representative of this astronaut, cosmonaut population that is the warm, fleshy body that is going to fly to space and to be exposed to this radiation environment. And so, I can't speak with expertise about this, but I can say that from the perspective of a crew member who's going to participate in these missions that are important, that we should be doing, both the short-term ones or short-duration ones we did with shuttle, the long-duration missions we're doing that are on the 6-month and 1-year kind of time frame that we have to look forward to on the space station, and for our future that I think we're all hopeful for in getting outside of low Earth orbit. This is one of, if not the top consideration that's out there. I think the word that comes to mind for me, though, when I'm posed with this kind of question about what do I think as a crew member in terms of radiation exposure, is uncertainty. And it's uncertainty from the standpoint of what we've heard already here today, in that it's not a totally understood phenomenon. It's from this perspective of what we're being exposed to in general in the environment and how that exposure affects us. And so I tried to jot down, I think, from an uncertainty standpoint, as a crew member, we have this pre-flight consideration. And every crew member wants to fly in space. And wants to fly in space more than once, I think. And because I think once you go, you cannot help but want to go back. So there's that basic, what is the clearance requirements in general? How do I even get the check mark in the box that says I'm cleared to fly short duration or long duration? And long duration being, am I good for a 6-month flight? Am I good for a 1-year flight? If I come back from that 1-year flight, can I fly again? And what impact is that going to have on me from a career standpoint, as well as just from my long-term health standpoint? I think there's the pre-flight considerations of participating in research that's being suggested. I know that every crew member that I've spoken to wants to participate to the maximum extent possible in the research activities that are going on board the space station. But some of these things will further limit us in terms of our ability to fly again, and as well as that long-term health standpoint. I also think that there's the consideration for the procedures, the medical procedures that we do just on a normal basis that feeds into that clearance for flying, which in some cases may actually be putting us in a worse position for getting that check in the box to clear us to fly. There's the on-orbit consideration. I think once you're cleared to fly and you're on orbit, the best that you can do is know what are the precautions and the protections that we can take, and how do we minimize that exposure to the maximum extent possible. I think there's uncertainty associated with that. As a female crew member, I got advice from earlier crew members that said, hey, there's these water bags. You can line your crew quarters with that. It helps. You might want to choose this crew quarters on board station because it has less of an exposure risk than others. And from my standpoint, it was really kind of going into that with the naive understanding of it. It wasn't an expertise associated with it, but it was taking the advice of others who had flown before me and had utilized whatever protection methods were available. I think there's also the post-flight consideration. There's what are the exposures that I saw while I was on space station? How is that going to be communicated to me so I can understand that? Will I get to fly again, short duration, long duration, and how is my long-term health going to be affected? I think also, in general, there is this aspect or this consideration for quality of life and being presented with the information in a way that while there's uncertainty associated with it, that you can get some consistency in the presentation of that material so that even though you might have that check in the box that says you're eligible to fly again, does that make sense to you as an individual, as a human being who is going to have to live out the rest of your life with the risks associated with that exposure? And so I think uncertainty is the point, as you can tell, that I'd like to get across today. I think we've had a lot of discussions in our office about how do we present the guidelines that are out there so everybody understands them. How do we present what it means to have that check in the box that says you're eligible to fly? And that's with the understanding that there's always going to be changes to this because of that uncertainty associated with the environment itself. And so as a crew member, those are my questions. My questions are, what are you using as the guidelines to assess eligibility to fly? How does it play into the medical procedures that you're using to make that assessment as well? And what is the long-term implication of the exposure I've had or the exposure that I could be presented with if I were to fly again?
Great, thank you,
Thanks.
Nicole. So I think what we've heard so far from Dr. Ushakov, Dr. Shavers, and Ms. Dodd is that the missions will be limited by the exposures, which we already know. There is uncertainty, not only in the science, but uncertainty from the crew office on the information about the exposure and what the clinical outcomes mean. And the request for more clarification on the guidelines on how we're going to move forward with this. So I'd like to throw a further wrench into the mix and ask Dr. Schwadron to talk about his recent findings that may affect the permissible exposure limits for not only future ISS missions, but exploration class missions outside of low Earth orbit. Dr. Schwadron.
Thank you. So first of all, I just want to say that this is a huge opportunity for the scientific community. There's a link between what's happening physically in the physical environment of space and biological systems that ultimately results in cancer, mutation, and evolution. And those are all components of life that we currently don't understand. So this is an enormous scientific area of discovery. One of the fundamental themes of what I've come to understand and wanted to tell to you is that by understanding the radiation environment and its biological effects, developing deep quantitative understanding with direct measurement, we actually buy trade space. It's the opposite of what you expect. There is undue conservatism because of lack of knowledge. And as we start to fill that in with detailed quantitative information, we actually begin to open up the trade space and help to potentiate missions well beyond Earth orbit and possibly to Mars. A little bit of background about our space environment currently. What we're seeing and what we've been seeing in the space environment since about 2005 has been fundamentally different than what we've seen throughout the rest of the space age. The sun is quieter today. It produces releases less magnetic disruptions in the form of coronal mass ejections than we've ever seen. For example, during this last solar cycle 24, a time in which we should see the sun being very, very active, we saw many, quote, spotless days in which the sun had extremely little activity. So as a result of the sun becoming less active in this very unique space environment, it produces smaller amounts of weakening magnetic fields that actually lead to higher fluxes of galactic cosmic rays. Galactic cosmic rays are coming into the system from outside, and as the sun produces less and weaker magnetic fields, the galactic cosmic rays can better penetrate the system. That means that anyone venturing beyond the protective boundaries of the magnetosphere, our own Earth environment, will have to deal with higher fluxes of galactic cosmic rays. What we're finding is, when you take into account risk, that leads to reductions of on the order of 30 to 50 days, safe days in space. However, I want to qualify that what we've published so far, what we've come to understand about the space environment so far, does not take into account all the details of the space environment. Again, another specific example. If you look at the periods of solar activity over 11 years, and we continue to see typically an 11-year cycle on the sun oscillates between periods of relatively little activity, where it's not releasing strong magnetic fields, and much stronger activity. During the periods of little activity, you have much higher fluxes of galactic cosmic rays, and as a result, that helps to limit the number of days that crew members can be, quote, safe in space. During solar maximum, the sun releases a lot stronger magnetic fields, and that helps to reduce the fluxes, and astronauts can be safe for much longer. And the effects here are very dramatic. For example, for a 45-year-old male in 2010, they were typically, the number of safe days was about 350, okay, about a year during solar minimum, whereas during solar maximum, it was something between like 900 and 1,300 days. Okay, so that makes a huge difference in terms of how long you can be out in space and what you can achieve as a result. Those detailed considerations, and I don't think that those specific numbers are useful except to exemplify the point that by developing more quantitative information, we can better achieve the goals that we're trying to achieve. That fundamentally is what we need to be doing in the future. So with that, I'd just like to mention a few things where I think that we have to improve our knowledge and our understanding and the mechanisms by which we do that. We've made a tremendous investment over the years in modeling, and we have developed a very good capacity for modeling the biological effects of galactic cosmic rays and solar proton events. Validation with direct measurement leads to enormous discovery and enormous changes in our understanding. Those direct measurements are fundamental. And it's not only in space where we need direct measurements and the direct measurements of radiation effects, but it's also in the laboratory. And it's making the direct link to animal models and ultimately to our understanding of human systems that can lead to better estimates of risk. I know that I'm running long and that this is running long, so I'm just going to conclude to say that the current situation that we have in space is limiting in many ways. We're trying to do more than we thought possible with the resources that we have available. Highlighting that point is our monitors in the near-Earth space environment, what's called L1. We have a number of assets that have been absolutely critical in providing the information that we currently have about our space environment. Those assets are aging, and they will retire in coming years. We have to figure out ways to replace them in order to continue to enable the exploration that we're going to be doing. And that's not just at L1, but as we venture towards Mars, we're going to need to develop an interplanetary asset that really can monitor and even predict that space environment. And there are missions that are ready to go that are not all that costly to do that. So I will end there. I will say that our developing understanding is considerable, and it's advancing very, very quickly. It's important that we continue to advance it, because as we do, the trade space for exploration actually opens. It doesn't close. Thank you.
Great. Thank you, Nathan. So it is important to measure the radiation environment to be able to validate the predictive models, and measuring radiation isn't exactly straightforward. So I would like to take this opportunity to ask Dr. Rosenfeld to talk about the importance of measuring radiation for dosimetry and risk assessment, and how it will or could be done during long-duration missions based on the limited mass and volume of a spacecraft. How do we get the hardware and the technology we need to fit into the much smaller vehicle? Dr. Rosenfeld?
Thank you very much, Jeff. First of all, I would like to thank for kind invitation. I'm very happy second time to be member of this panel and contribute to all astronauts to make sure that we're measuring what makes sense. As we discussed today, certainly radiation environment is very complicated. In contrast to our visit to dentist, where we're dealing only with X-ray radiation, space environment mostly based on charged particles and neutrons. Well, different kind of charged particle depends on orbit. If we're talking about deep space, we're talking about heavy ion with energy 1 GeV per nucleon, 10 GeV per nucleon. If we're talking about travel to the moon, we're talking about mostly protons and neutrons. Well, it's so named mixed radiation field. It's very nice, certainly introduce dose limit. We can talk about dose during the career. However, what we're measuring? We know that it will be good not to have more than 0.5 sievert. If we're talking about sieverts, it's a dose equivalent, which dose equivalent in contrast to absorbed dose, which related only to energy deposited per 1 kilogram of mass. Dose equivalent taking into account radiobiological property of radiation. So we need to know how different organs, how different parts of the body react on particular environmental radiation environment, mixed radiation environment. How we're dealing at the moment? Well, you need to know energy deposited on a cellular level. Finally, we are damaging cell, we're damaging DNA. So current concept, which really corresponding dose equivalent, is so-named microdosimetry, when we're talking about energy deposited on a cellular level. So you need to be capable to measure this energy. How we're doing now? So currently we introduce tissue equivalent proportional counter. They're quite big, massive. They demand gas. They demand 2000 volts. They demand change pressure of gas. I'm not sure, I would like to say I'm sure that it's not convenient to have tissue equivalent proportional counter on a spacesuit. It's simply impossible. We need to do something which make astronaut comfortable, lightweight, and with RF capability, wireless capability to measure dose in real time. So at Center for Medical Radiation Physics, University of Wollongong in Australia, we're working last 16 years to develop for astronaut portable dosimeters, which measure really radiobiological dose. It's so named microdosimetry. And we went from tissue equivalent proportional counter, huge counter, to very small silicon chips. So what we're doing, we're modeling biological cells with silicon cells with similar size, and we're capable to measure energy event by event from all charged particles in this particular two-dimensional array of cells. So why it's important? Because such kind of dosimetry absolutely independent on radiation field. Doesn't matter what kind of radiation field produce secondary particle. Secondary particle from a wall of aircraft, from our body. So if you're capable to put your dosimeter and surround by material of interest, material of lung, material of muscles, bone material, you will get secondary particle which corresponding real situation. And you're measuring energy deposited from this particle on micron scale. Saying that, it's not simple problem. Not simple problem. First of all, if you're doing based on silicon, you need to be able to convert to tissue. So we develop very complicated software and very nice software which converting silicon to tissue. We're capable now produce with modern electronics array of micron size silicon cells which can be read out with readout chip on the same detector. So in this case, you're capable to measure starting from 0.1 keV per micron, its energy deposited per 1 micron, and up to 1000 keV per micron from heavy ion. Additional problem here that radiation field is different if we're talking about solar particle events, or are we talking about deep space? For example, a result of interaction of heavy ion with spacecraft, you can produce secondary particle with very low energy. For example, alpha particle. The range of alpha particle in the body 27 keV, 25 keV, 5.5 MeV. They produce enormous effect on skin. So you need to measure skin dose. So what does mean this? If your detector, like usually we're using wearable detectors, they packed with piece of plastic. It's simply this plastic not allow alpha particle to come to the detector. You never will be taken into account. On the other hand, astronauts will be irradiated by low energy ions. So it means you need to have a different packaging, you need to have different converter based on bone, based on muscle, based on lung, and it's a very complicated problem because do not exist plastic which representing lung, do not exist plastic which representing bone, do not exist plastic which representing muscle. Such plastic exists only for dentists, for X-ray, which based on electronic density, but it's not composition exactly like bone. It means neutron is not going to produce the same secondary particle. So it's a whole story. What I would like just to ask you to think not only about threshold limits for astronauts. We must be sure that we're capable to measure what we're talking about. Otherwise, we're talking about apple and bananas, which is impossible to compare. Well, another interesting story which going on now last 10 years is development nanodosimetry. We came to conclusion the microdosimetry, which important on cellular level, not enough as well to predict damage, biological damage in astronauts. Why? Because finally we're damaging DNA. You need to know ionization on a level 2 nanometers. Can you imagine detector 2 nanometers? It's quite difficult. However, we come up with very interesting ideas using nanoparticles to produce nanodosimeter, which actually working on nanoscale level. It's a very interesting project which we are doing now, and certainly everything was possible due to enormous support financial from NSBRI, which we're working jointly with US Navy Academy and with NSBRI and Memorial Sloan Cancer Institute in Manhattan to address this problem. Actually, all our activities came from radiation therapy. Our center, Medical Radiation Physics Center, which working in proton therapy, heavy ion therapy. We're doing a lot of collaboration with HIMAC, National Institute of Radiological Science in Chiba, Massachusetts General Hospital proton therapy, Loma Linda proton therapy, and a lot of common between treatment cancer and study radiation which can produce cancer. So I just would like to thank NSBRI again for strong support during the last 6-7 years, which led to development such microdosimeter. Currently, we're developing final stage microdosimeter with a RF chip. Everything will be in one chip, which is capable to communicate with main station. And I hope within a couple of years we'll get a very nice detector and will make happy our astronauts. Thank you.
Thank you, Dr. Rosenfeld. Dr. Hines, I'd like to ask you to discuss how, in your research, the animal models have demonstrated different susceptibilities to the effects of space radiation, which could point to a phenotypic differences that could possibly lead to the development of biomarkers for countermeasures. Could you talk about that quickly and what you have seen?
Sure. Certainly. Our research has been looking at the effects of radiation on the central nervous system or the brain, and mostly in rodents. What we are looking at primarily are the acute effects or the short-term effects on the brain. There are already known that there are a number of effects of radiation. This includes inflammation, oxidative stress, changes in synaptic excitability, changes in the dendritic structure, and so on. What's not clear from a lot of these studies is how do those effects impact behavior? How would it impact the performance of an actual astronaut or a cosmonaut? So one of the things that our research has done is to actually look at performance on a task that's very similar to what an astronaut would do. And for this, we've taken a task that Dr. Dinges and his colleagues have developed over the years, the psychomotor vigilance test. It's also called the reaction self-test on the ISS, where it's available for astronauts to perform. We've taken this test and trained rats to perform the exact same test and get the exact same kind of data. And with this test, we've been able to demonstrate that particles such as high-energy protons, iron ions, silicon ions, all produce deficits in this type of performance. Those particles can slow reaction times, they can produce lapses in performance, they can produce what's called impulsivity in performance and lower the accuracy of the performance. And they do this at relatively low doses. We're talking about anywhere from 5 to 25 centigrade. These are single doses that do this. The surprising thing, though, is that we see individual differences or a differential susceptibility to these effects in our rats. So that some rats will be exposed to a relatively high dose and show no effects. Other rats can be exposed to the same dose or even lower doses and consequently show effects. So we're seeing this differential susceptibility, and I have talked to a number of colleagues about this, and they are slowly starting to see that in their other procedures as well. One of the things that we've been able to do so far is to look at brain tissue in these animals and discover that there are differences in neurotransmitter function in the animals that show these effects, whereas the animals that do not show these effects do not show these changes in neurotransmitter function. So these occur at relatively low doses. One of the problems with this, obviously, is that we're dealing with a single dose. Most animal studies just give one dose of radiation to simulate what an astronaut, for example, might be exposed to over 2 years on a mission to Mars. So there's a vast difference in the way these studies are done. Additionally, we typically do not study male versus female, so we don't know much about those types of differences yet. So there are a number of differences like that. The other problem with a lot of these procedures is you don't exactly know what's going to happen. How do you translate going from the performance of a rat in a box to the performance of someone on the International Space Station or in a capsule heading towards the moon or someplace else? So it's a vastly different complexity of performances that we're talking about. And another problem with these studies is the fact that rodents in particular are not quite as sensitive to radiation as other animals, and presumably humans and others. So I think one of the things that really needs to be done here is there need to be more studies that go to a higher level in terms of looking at cognitive function in these kinds of things. One thing that's on the drawing boards right now, I think there are movements to do some primate studies in this regard, which would certainly help. But one of the promising things, I think, is the fact that since we are seeing individual differences, we may be able to, at some point, come along with a biological marker that indicates this. Some of our studies right now that are ongoing are trying to do this precise thing, and that is to look at, for example, neurotransmitter function in different strains of rodents where the function differs. We're looking at pre versus post-exposure differences to see if we can tell ahead of time whether or not there may be some way to identify an individual that may be more resilient to the effects of radiation, or another one that may be more susceptible to those kinds of effects. So those are the kinds of research we're doing right now.
Great, thank you, Dr. Hines. So I know that we're running short on time, but I think we have one more big question that needs to be addressed. So we have learned that the permissible exposure limits are limiting out of necessity, but they may actually limit the duration of future long-duration missions, even more so because the GCR fluence could possibly increase over the next 5 to 10 years, which could be more problematic for these limits. We know that the astronauts, they would like more information about the clinical outcomes. How are these exposures going to limit their career as an astronaut and possibly affect their long-term health? So there's less uncertainty in that aspect. And then their research community, for the radiobiology research community, is showing that there are outcomes that point to possibilities for personalized countermeasures. So before we open up the panel for questions and answers with the summit, I would like to ask Drs. Bogomolov and Dr. Jones to tackle the one big question and discuss how, even though the current radiation risk is difficult to associate with clinical outcomes, can you talk about the utility of being able to provide a medical diagnosis or an exposure-based clinical outcome for future long-duration missions? And Dr. Bogomolov, would you like to?
Я очень рад, что наши коллеги из России могут быть с нами на этой конференции этот год. Мне очень приятно увидеть вам сегодня. I'll just make a few comments about what Jeff asked us to discuss, which was the ethical need and the operational need for this topic to be researched. And I think it's very important. And Jeff probably doesn't realize, saw Mike Barrett here, we spent a lot of effort in the early ISS days working on this administrative limit concept and trying to define an area where we would try and reduce exposure, but at the same time not have a hard limit so we could balance the risk associated with crew training versus potential exposure. And it wasn't designed to be necessarily something that would prevent the crew from flying, Nicole, but instead to give them some kind of informed consent about what their risk would be and let them make a decision about future assignments. Whereas the legal limits are something, that are national guidelines that the nation has agreed to that should be based on health and safety concerns. And as Dr. Usachov and Shavers both pointed out, none of our crew have really come close to reaching those career limits. But those limits are not really appropriate for future missions for exploration class flight. And as we've heard from Dr. Zeitland in his recent paper on the measurements from the Mars transit exposure, we think 0.8 to 1.2 sieverts is going to be pretty close to the exposure for just the Mars transit phase. And so a 3-year mission may push us well beyond our current career limits. And when we're talking about particle tracks, and it was mentioned earlier by Dr. Rosenfeld that the high Z exposure is really what we are fearing, because we're talking about particulate tracks that are primary energy deposition plus a penumbra of fragmentation products, neutrons, delta electrons, spallation products, et cetera, that potentially have much greater biologic effect than we've ever really studied well with low LET radiation. And we don't know what those long-term effects are going to be. So we really need to implement that ALARA principle that Jeff talked about. So how are we going to do that? And Eddie Simonis couldn't be here, but I remember many times sitting on console with Eddie and during shuttle and ISS missions and trying to convince the flight director about potentially delaying an EVA because we had increased geomagnetic activity. Well, we need to find flight rules for this, and it's really hard when your principle is only ALARA. So we need to find operational limits that we all can live with and we can all enforce when it comes time for protecting the crew. And part of the problem is the uncertainty in what the biologic effects are going to be when we get outside of low Earth orbit. And so we need better and more focused research currently on the ISS. We realize that now most of the research is being done on the ground with particle accelerators and cells and animal models, but I think it's imperative that we use the ISS for human studies while we have this great opportunity. These crew are going up there and exposing themselves to radiation that's far and above what any IRB or CPHS would allow us to expose humans to on Earth, and so we really need to take advantage of this, and we ought to use every possible genomic, metabolomic, proteomic study that we can implement to understand the effects while these crew are flying and look at the potential role of radiation protecting agents. We also need to consider that because the likelihood of acute radiation sickness is pretty low from an exploration class mission, we expect more likely would be prodromal type symptomatology that could develop during one of these missions. We ought to do some additional research on how we can affect prodromal symptoms and research on agents such as serotonin, dopamine, histamine, or substance P antagonist. But I do think that there's an opportunity now with the ISS to do this kind of work, and we ought to take advantage of it. And we clearly need operational limits that are enforceable, that all have agreed to, and that have a clear scientific basis for us to go forward.
Thank you, Jeff. Dr. Bogomolov?
First of all, I would like to agree with what was being said with Jeff regarding radiation effect or radiation impact. At this point, we still don't know a whole lot. I would say that we really don't know the majority of the information that we need to know, and the limits that we're using right now are administrative in nature. They are based on administrative reasoning theory and not really proved yet. So it's some sort of a compromise between the real radiational loads that exist and our current capabilities to reduce their impact. Therefore, it is very important to study radiational sensitivity. It can vary not just between various species, but also between different people. Therefore, latent effects can be different for different people, bearing more risk of cancer, cataracts, and so forth for some, but not for others. Because there will be some people who will have no serious problems because of radiation exposure. And that pertains not only to astronauts, but also to those who were responders to Chernobyl disaster. Therefore, I think that this type of research, the research on radiological sensitivity, is extremely important, and it will give us much better basis for selection. However, overall, our major goal is to limit radiation effect, radiation impact, and to minimize radiation effect during flight and during various research and tests. The only thing I would argue is that most of the issues related to radiation can be resolved using ISS resources. ISS is located on the very low orbit, relatively speaking. It is protected by the magnetic field from the Earth, and therefore the results that we will glean from that research will not be most accurate. So in terms of what we can do right now, it boils down to primarily monitoring. We are not yet in control of this process. Although we do have some control when we talk about EVA or advising crews to go to shelter during solar activity. So I think that now that we talk about our future and long-duration flight, interplanetary flights, we should also be seeking new ways of protecting human life and health. Perhaps we will have to create some kind of artificial magnetic field or do further genetic research and studies pertaining to radiological sensitivity. I'm not an expert in this field, of course, and what I'm saying on the subject may not be exactly professional, but I do think that all of this is important for human health. Thank you.
Thank you, Dr. Bogomolov. I think at this time it would be appropriate to open up the floor to questions and answer. But before we get started, I think in the spirit of the international cooperation that is needed, that Dr. Ushakov stressed, I would like to provide the opportunity for one of our other international partners to answer questions from the perspective of the European Space Agency. So Dr. Straub, if you're willing and there's questions that are directed toward the panel that would you could provide insight out also, I would invite you to join us. So with that, I would, if you have any questions, please feel free to ask the panel. I can answer that.
I would like to segue off the last two speakers' comments. Dr. Jones suggested we need to utilize ISS more to gain valuable information on those crew members currently exposed. Certainly that would seem to make sense. But then Dr. Bogomolov points out this is still very low Earth orbit, and it may not tell us as much as we need to know, of course, about true exposures outside the magnetic belts. With those, so we have some tension between those two perspectives. What might be the value? Do you see any value of pursuing more aggressive investigation on ISS with cell culture or animal work? Is there a place for that? Is it helpful in that actual space environment, even though inside the magnetic belt?
Thank you. Thank you very much for your question. I'm all for expansion of our current research in the area of radiation on the ISS. And I know that this research is ongoing, which is something Dr. Ushakov was talking about. We have Matryoshka experiment. We have tissue equivalent models that allow us to study the impact of various radiation doses on deep tissues in brain, eyes, and so on. These are all very important types of research in terms of safety. We're also studying the dynamics of radiation on the space station, because the space station is very large, and we can see how it is impacted, and maybe it's impacted differently. And that allows us to do better design in terms of wall thickness for the space vehicles. However, it is impossible to model in low Earth orbit types of radiations that will affect our crews during the interplanetary flights. This type of research or studies would be better conducted here on Earth, where we can simulate the galactic rays, proton radiation, and so forth. And here on Earth, we can design various protection measures against those types of radiation.
Можно я
That's all I
тоже-
have.
Можно я тоже обсудить это?
May I also add a few words?
So I think that he brings up a good point, and I said I caveated mine that most of the work, and it comes to high Z radiation, is going to be done on particle accelerators here on the ground. Obviously, we know that, but unfortunately, we can't expose humans to this radiation. It would be unethical and really financially impossible. So what are we going to do in the meantime? And I think that there is a lot of very good information that can be gleaned because the radiation exposures are so much higher in space than they are on ground for any human system. So when we're talking about the effect of potential protection agents on the human, this is the only platform we have to do the research right now is on the ISS. And I think hopefully Mr. Gerstenmaier's listening. But I think that, so we need to take advantage of it while we can. Now, admittedly, there's going to be additional work that has to happen beyond the low Earth orbit scenario, and that is obviously why we have a range of research projects that are going on that are nuclear or particle accelerator based, and we have to have that.
The largest uncertainties definitely are associated with the biological responses, and these studies can be best performed on Earth at particle accelerators where we can detect and monitor the radiation fields and prescribe them. It won't ever mimic space radiation environment, but we're getting more and more space-like beams. More and more we have a systems biology type of an approach, but we just don't have the evidence base to use yet to inform our risk modeling. Our latest risk models now include particle species and energy in part, so track based risk. But we're not there yet with having a systems biology answer. We're still using epidemiology to its very limits that we can to inform us about the risks of the GCR and trapped particle environment in space and SPEs. And I think that we'll continue to rely upon ground-based experiments very strongly to reduce the largest uncertainties. With regard to detection that was talked about, we need these detectors very much to normalize our models of space radiation, that are the radiation being transported through the vehicle and into the body of the crew member. We've got to have good models of what that environment is, so those detectors are needed.
I think I saw a question.
Here. Up here. Thank you. You were talking about the physiological aspects of the exposure. Excuse me. And that was very interesting. Dr. Ushachev is the only one that made mention of the reduction of that to inside the spacecraft. Are any of you working with methodology, or do you think enough effort is going on towards reducing the internal exposure as opposed to just dealing with all the aspects of it?
I can provide you our experience with space station. This is the first time we've designed shielding expressly for the purpose of protecting our crew members. Our early astronauts, including at least one of the female astronauts, did protect herself by having plastic shielding around her. It turns out the hydrogenous materials are much better than high Z shields like we use, for example, lead here on the ground. And now we've got crew quarters which are lined in part to a great extent with polyethylene, very hydrogenous material, and it's very effective at reducing the trapped proton radiation. When we go out beyond Earth orbit, we've got these highly penetrating particles which cannot be stopped with any reasonable amount of shielding. Our models that transport to these very, very thick amounts of shielding provided by the vehicle and its contents and the human body itself grow uncertainty with path length traveled. So we're now back in the realm of uncertainty.
I was not talking about individual protection. I'm talking about protection of the spacecraft, the vehicle that they're traveling in. Any of you working with that? Do you think enough effort's going into that? Because frankly,
Getting there faster, right? You're talking about getting there faster, right, Walt? I mean,
well, getting faster is one of them, but also I don't think you're going to get there that much faster, so you're going to have to live in that environment, and you're going to have to find some way of protecting the spacecraft if you're ever going to make it practical.
Well, in the distant future, we certainly can get there faster with nuclear-powered propulsion. That's not a high priority funded issue now here at NASA, but that certainly would reduce our human exposures and the electronics exposures. And this is a real problem. We've lost radiation detectors due to radiation. The smaller, faster, cheaper that we get, we end up having very small problems that end up being very large problems with our semiconductors. And we do have models of interactions which cause latch up and single event upsets and these things.
Dr. Schwantner, you had mentioned toward the end of your presentation the issues with respect to the assets that we have at L1 and the criticality of those. You also mentioned that we need an interplanetary monitoring capability, and sort of ended with, and perhaps you could elaborate, that we have missions ready to go, but I wasn't sure whether you were inferring that we're in shape for this missions ready to go for interplanetary, or again, whether more were needed to actually get the type of monitoring that you're suggesting we need.
Thank you. Yeah, let me just, I think your question really requires just that I elaborate on the points I was making. So first of all, with respect to L1, ACE is one of the critical assets there, and that is incredibly above its performance lifetime. We all hope it's going to live a lot longer, but many of the detectors are starting to show the real effects of aging. So ACE is a critical asset that needs to be replaced. There's two different missions currently that are both ready to go, in the sense that, well, one is essentially what once was Triana, and is now the Discover mission, and that is very much ready to go. That would provide bulk monitoring of the solar wind, okay, so it's not going to do much for radiation specifically. There's another mission that was recommended by the Heliophysics Decadal Survey, one of the highest missions, highest ranked missions in that decadal, and that's called IMAP, and that is a very complete replacement for the capabilities of ACE, including the radiation monitoring. So I think it's very important to get that asset in place as soon as possible, so that we don't lose any capability. The second component of that is, in the future, as we look towards interplanetary missions, what additional assets are we going to need? One of the first things I think that we're going to need to think about is an L5 mission. This provides both prediction, in the sense that you're looking at the part of the sun before, as events come that would then travel and get to Earth. And then the second part of that is to have observers that are distributed longitudinally in the ecliptic plane. And one of the questions that people often ask is having something at 1 AU sufficient? And the answer is yes and no. I think for much of what is needed in the interplanetary space environment, the answer is you could do a heck of a lot with longitudinally distributed observers. What we've shown with being able to model energetic particle radiation from the sun and galactic cosmic rays, that with those longitudinal assets, we can actually do very, very well for modeling the environment. Ultimately, having missions further out would be valuable too. But I think that's that stepping stone approach. L1, let's shore up L1, L5, and then longitudinal distribution of observers is the right approach.
Great. I think we have time for two more questions, and I know Dr. Young, you were been waiting, so I'll pass it over to you.
Really following up on Walt Cunningham's question, and it's a broad one. We have a problem. We have a problem without a solution now. Those of us who go and speak about going to Mars are almost always faced with somebody who says, how can you dare do that because of the radiation risk? Okay, so you have mentioned, by my count, 6 potential areas for protection, right? Passive shielding, active electromagnetic shielding, trajectory alteration with faster interplanetary travel. You mentioned or actually have not talked about the pharmacological benefits, the developing pharmacology, the individual selection of the astronauts for low susceptibility subjects, and the detection of times when there will be low hazard. Could you give us your opinions about the high probability areas, the ones in which we should be putting our best scientists and some of our best money into trying to solve this problem?
So can I just add one quick addition to that is timing. Timing is critical. As I mentioned, mission going towards during solar maximum in the current environment, what we're seeing is relatively low probabilities of large SEPs, and we're also seeing strong reductions in GCR fluxes in solar maximum. That's another protection, actually. It can change the number of safe days, increase it substantially.
But that also has to be timed with the best trajectory to get to Mars in the shortest possible time.
I agree.
And you have narrow windows that really allow you to do that.
I agree.
Yeah, it's going to be
But
rare.
Dr. Young, we did mention radio protection. That was part of what we talked about. And I think that is a very important area that we need to work in. Certainly that has shown some promise in low LET radiation. The question is whether we can have any beneficial effect in high LET radiation. That's a big question mark and a big area of concern.
Jeff, you're speaking of pharmacological protection?
Yeah, there's a whole host of potential agents that could be used, ones that either reduce the effect of the secondary products, and we're talking about ionizing events, reactive oxygen species, lipid peroxidation, et cetera. So we can measure those things and we can look at the ability to attenuate those things with agents. And the other potential aspect is looking at cell death, things that would be apoptotic events versus those that will be mutational. And can you reduce those that would be mutational in nature that would not induce an apoptotic event? So yes, absolutely.
I'd like to.
Я бы добавил к вашему.
I would probably add, I would probably rephrase your question. You were talking about priorities, and I would talk as to what is least studied. If electromagnetic, some protective physical aspects are more or less clear to us, then the questions on individual radiational sensitivity, pharmacological involvement, those fields are not studied practically at this time. I think this is where I would put our efforts.
But Dr. Bober-Groff, have there been any advances in practical electrical or electromagnetic shielding of the spacecraft? Do we have reason to hope that that's a practical solution?
In any event, these activities are ongoing to create artificial electromagnetic field around the vehicle. This is a physical type of problem, and we do carry out this research, yes. And we're designing this Marshall vehicle also. That will incorporate.
Maybe you could get two in one by having a better vehicle from a transit standpoint that may also generate enough power to allow an effective electromagnetic shield, because right now the power levels are not high enough to really make a dent in the level of physics that we're talking about with these high Z particles.
And as long as you're at it, spin the spacecraft to give
Absolutely, I'm with you there 100%, my friend.
I think the most recent design studies have shown that an active magnetic shield would be most practical for a planetary surface like the Moon or Mars. It'd be very, very difficult to do for many different reasons for a vehicle. With regard to timing of a mission, that's going to be very difficult to ask a program manager to wait until it's the right time to go. It's just going to be very, very hard, I think, to ever do that for an exploration class mission. With regard to pharmacology, the challenge would be to demonstrate that by taking a drug either before, during, or soon after a transient event of high exposure, such as an SPE, is efficacious and actually helping in all manners to the entire human. So something that might protect the lung or breast might be very detrimental to the prostate or something else. So that's going to be a big challenge. I don't think we're anywhere near ready for that. Some of the pharmacological agents have a performance decrement that is just completely intolerable at the dosages required. And always the best solution is to reduce radiation exposure so that such measures are not needed.
Okay, thank you, Mark. I think we have run out of time. I think myself or any of the panelists will be happy to discuss this during lunch or on some of the breakout sessions. I'd like to thank our esteemed panel and the audience for listening. We appreciate the opportunity. Thank you.
If the one-year panel would come forward, we'll go ahead and get started on the